Okay, so we've got a few more people now signing in, so I think I will not delay things and get everyone going. So welcome to all of you, and thank you for registering and then joining us today. This is part of a series of webinars that we host roughly every month at Synaptec, where we try to explain some of the core features of our technology platform, or indeed the applications and benefits of them, particularly at the moment in transmission and distribution networks. And today, we are wanting to talk to you about cable fault detection because this has come up several times recently, and people have asked for more information about why it's needed and exactly how we deploy and operate. So this is also in response to several questions from customers about how to do this. And as I go through the slides here, I'm going to introduce both myself. So I'm Saul, and I look after sales and marketing and everything relating to customers at Synaptec. And I'm joined by an expert witness, which is Dr. Neil Gordon, who is our head of mechanical sensing technologies and basically how our systems work. And Neil will be taking you through part of the functionality today. So our agenda for everyone today, very quickly, of course, I have to explain for some newcomers, and there always are in these webinars, what Synaptec is and why this technology is unique, how we do it differently. Then we'll be talking about some of the challenges relating to the undergrounding of transmission and distribution lines and why the instrumentation of hybrid or mixed circuits is particularly challenging. And then, of course, we can also talk about how we differ in our approach to cable fault detection and some of the benefits that derives. And hopefully at the end of that, that will enable us to share more insights, make sure that you're well informed, give you access to other content that's available online or we can supply after the call. And if we've got a reasonable amount of time at the end of this, we'll also be keeping an eye on the controls here for Zoom and looking out for any questions that participants may want to ask. Now, in that regard, you'll see that the chat channel isn't working, but there is a Q&A channel where you can ask questions, and we'll keep an eye on that and do our best to answer them. If Neil and I can't answer any of those questions live while the other person is talking, we will, of course, record and keep all of these questions and try and feedback. We always respond to everyone who asks a question, but it might take us a couple of hours after the meeting is through to get back to you. So please be patient, because sometimes we get floods of questions at the end of these sessions where we have to explain. Anyway, so with that in mind, let me first introduce us and Synaptec for those who don't know. We're a company based in Glasgow in the UK, and in essence, what Synaptec invented was the world's first distributed sensors for electrical power systems. And in plain English, this means we found a way and patented it, and now we're selling it, and it's deployed in transmission systems around the world, where we can measure current or voltage completely passively. That means we don't require power supplies or data networks to operate our sensors, and this is what we call distributed electrical sensing. Now you'll see here I've deliberately called it distributed electromechanical sensors, because we can combine in the same system and on the same technology platform the synchronous measurement of current or voltage and various mechanical parameters, which we'll show you in a minute. Now this notion is a network of passive sensors which are connected only by optical fiber. So this is an ideal way to leverage the existing optical fiber that you have in most high voltage transmission systems, where the fiber is contained and passed along the OPGW or the neutral wire. And our mission as a company is to help power system operators reduce the capital cost of instrumentation, as well as bring new information and data insights which will help reduce operational cost of that visibility and control. And as you can see across the bottom here, there's a range of customers who are already working with us, going from Scottish Power and Statnet, which were focused on digital substation innovations, through to SSE, which is about instrumenting very complex circuits over wide areas, through to Vattenfall, which is our first offshore wind deployment, and now most recently Red Electrica in Spain, the transmission operator for Spain, who are asking us to help with underground cable monitoring systems. And Deutsche Bahn, that logo may be familiar to many of you, the German state rail operator, where we're applying our technology to help with measuring and monitoring their infrastructure, which is the 25 kV overhead power lines that they're operating nationally. But all of these things, they have one thing in common, which is about distributed sensors reaching a long way and leveraging existing optical fiber as a network to provide more insights. Now, many customers have asked us to explain this, and we're trying to take care at a simple level here to explain why this is different, because our distributed sensors are not optical CTs. They're not, sometimes they're called low power instrument transformers or LPITs, sometimes they're called zero power or non-conventional instrument transformers. These are shown on the right here and are typically used in a substation, maybe for a metering application where you want very, very high accuracy, but they're using the Faraday effect where you're winding a fiber around the conductor to polarize the light and get a very precise current measurement. That is not how we operate, and it's not what we do. We're using that optical fiber for best effect because it's the gold standard for long range, low loss and high bandwidth telecommunications. And we're using that sensor as a network to put arrays of sensors out into the field. And in fact, the scalability of our technology is what takes us apart. So the concept here is that you'd have one active device inside the substation, normally publishing like 61850 sample values data directly onto a process bus or a station bus within the firewall of the operator's IT domain. But we're using a fiber to reach out a long distance, and we can serially multiplex or daisy chain a series of up to 30, that's 30 sensors over a range of 60 kilometers per fiber. This is the standard single mode optical fiber that's already available in most of these transmission lines or very nearby. So it's highly scalable in blocks of 30 sensors, and those 30 sensors could be any combination of current, voltage, or both, mixed in with temperature, vibration, strain, or indeed overhead line sag measurements. So we can synchronously combine many of these measurements and bring them together into one point to provide additional insights to a network. Now, these sensors, when I say they're not Faraday effect, you'll see here, they're actually industry standard CTs and VTs. They look like traditional standard CTs and VTs because they are. What we're doing is adding a passive measurement device to the secondary in the base or the output of these transformers in order to convert a electrical signal like a voltage or a current directly into a color of light which passes to and fro through the fiber. So the only thing connecting these remote sensors back to the base where they can be interpreted and published is different colors of light. And that's incredibly useful because it means we can go a very long range, and it also means these devices are incredibly simple and familiar. You don't need any new skills to install them. You will find that they're incredibly robust and accurate. And of course, the operator will tell us what accuracy class is required for the different applications that we use. It also means we can secondary connect, or we can indeed work with existing primary instrumentation that's in the location that you want to measure. But importantly for this application, these devices are self-calibrating for temperature effects, completely immune to electromagnetic interference, and very importantly, require no periodic maintenance or calibration. Once these things are installed, they will stay out there operating on their own without further intervention requirements for many years. And when I say many years, Neil's team have been doing accelerated lifetime testing in the labs here, which has demonstrated that we've had no accuracy loss running these sensors for over 140 years. Now, that's pretty reliable, but the real benefit is that capital instrumentation cost saving. If you have passive sensors in your network that no longer require power supplies, copper wiring, data networks to bring the signal back, 4G, power scavenging or batteries, recalibration, we don't need time sources and synchronization because it's done centrally, but you're saving all of the copper wiring and equipment and civil works that's traditionally surround the instrumentation that's needed to accurately capture a voltage or a current and bring it back. to a central point. So it's super efficient way to aggregate lots of data and bring it together and provide that data in a useful way from very long distances and probably from locations which are inaccessible or remote. So typically we will see our technology used in digital substations, in renewable generation, monitoring subsea cables, in a wide area monitoring with synchrophaser applications, or indeed monitoring overhead lines and underground cable systems to look for early warnings of failure or degradation of the conductor. We're doing a lot of work with complex circuit protection, and I mentioned rail, but today we're on the bottom right of this graphic here, and we're talking about cable fault detection, and specifically faulted section identification in cable sections which form part of mixed or hybrid circuits. So of course there are lots of reasons why operators choose to underground their cables, and what the challenges are pretty much captured in a white paper that's currently been published in Transmission and Distribution World. After this webinar, we'll provide you copies of these slides and you'll have the link to that, but it's easy enough to go to tndworld.com and find it under New Approach to Cable Fault Detection. There's a full white paper explaining how we help some of the challenges that are out there. But there is no denying that the trend is to underground more and more, and this creates mixed circuits or hybrid circuits in the network. To throw some interesting numbers for those of you that you don't know, in this country, we're based in the United Kingdom, there's recently been a very large fund offered to help transmission operators underground lines through national parks. There are almost 40% of new transmission circuit length now being installed underground in Scotland, where we're based, and indeed across the UK, National Grid's transmission network is about 20% undergrounded. There are, of course, some countries with less, and notable exceptions with far higher. Probably the best example in the world is just walk around New York and you'll notice that there are no overhead lines out there, because at the end of the 19th century they decided to underground everything because of storm damage. So we wanted to ask our customers recently in a poll where we had about 96 responses to give you a sense of this from different customers, saying, well, what are the key drivers for undergrounding overhead lines? Now, first, most popular response, I guess, is environmental considerations. So this refers to removing overhead lines and removing them from your line of view or the site of a particular area of national beauty or outstanding interest, or a national park, for example. And so the environmental consideration really is a visual or aesthetic consideration about cleaning up the view in somewhere that's deemed to be of national importance and very beautiful. Straight behind that, that was 34% of the vote. Directly behind that was simply avoiding obstacles. And I guess that's a very familiar thing for all of us, where you will need to underground a line because you're trying to bypass either a high density urban area, maybe the passage to an airport and runways, maybe it's avoiding a body of water or roads, but it's typically about avoiding some kind of obstacle. Bodies of water are particularly relevant, we find. And then you've got reliability and safety come maybe half as popular again to that consideration, but it is driven by some aesthetics, and it is driven by the avoidance of obstacles. And when we asked our customers, okay, well, what are the challenges relating to operating mixed and hybrid circuits? I guess this shouldn't be a surprise for anyone, but clearly our surveys and our customer interactions were telling us that number one is about fault finding. You know, was the fault underground or was it overhead? Because then you can direct resources to fix the problem with some confidence about where it is. Directly behind that is the notion of retaining auto reclose functionality. So typically in a mixed circuit, it would be ideal if you can distinguish between a transient fault, which is going to happen overhead and which allows you to reclose, and a permanent fault in an underground section that you would not want to reclose on. And the ideal situation would be to instrument that cable section separately and distinguish between overhead and underground faults, so that your post-event response is more targeted and appropriate. You can reclose with confidence when you know it's an overhead fault, and you can block the auto reclose command when you've got high confidence that it is indeed in the buried cable section. So that's a very popular requirement. And then generally there are, of course, there's not much in this, I guess, but there's some general, improvement of discrete response for protection and backup protection schemes. But that's what our customers have been telling us they need. And it shouldn't be a surprise to any of us that the considerations involved in underground instrumentation are significant because of the complexity and cost of fault finding and repair if there's a fault underground. But fundamentally, if you want to distinguish between overhead and underground faults, there are traditionally some significant cost implications where you're needing to do civil works, install power supplies and telecommunications at these transition points where the overhead lines come down and the cable section starts and then goes underground. And sometimes simply the access to these locations is a challenge because they can be very remote. And we've had interesting conversations with operators recently where the big challenge was that that transition point was simply so far away that they couldn't run LV cables out to power the system. And so they installed solar panels, which were being stolen by the locals and causing all kinds of problems. So what we thought the industry needed based on all of this evidence was a more scalable and simple instrumentation system that can reach out long distances, distinguish lots of different protected sections within a circuit, and improve the targeting and the response and the accuracy of the protection scheme to a fault, and enable that discrete auto reclose response, distinguish between overhead and underground. So at that point, with that being set up as the framing for this, I want to hand over to Neil, who's going to take you through some slides explaining what our approach is and how our technology is deployed in these scenarios. Neil?
Great, thank you, Saul. So I'm just taking control of the screen here. So our standard product for cable fault detection is rephase. Now that stands for remote fault sensing for the reasons that I think Saul's explained very well. So I'll be taking you through what the system looks like and its features for simple and quick installation on new circuits and for retrofit to existing circuits. Okay. So each rephase system that we have contains only two different hardware components. So the first one is the interrogator, which Saul's mentioned already. So this is essentially the measurement computer, and it's the only part of the scheme that requires a power supply and local time synchronization. Everything else in the fiber network is passive and requires none of that infrastructure. So the interrogator performs full differential protection to generate an auto reclose blocking signal. And that can be provided either in IEC 61850 Goose for digital substations or a simple dry contact for legacy systems. Now, as Saul's already explained, we can connect a large number of sensors to this interrogator, so it can be thought of as something like a super emerging unit because it collates measurements from a large number of sensors that are distributed along the existing fiber optic. And what this means is that we can also offer an optional sampled value kind of point on wave measurement output from the interrogator. So that would be the individual point on wave measurements from every sensor that is connected down that fiber optic. Now, the second hardware element that we use in this system is the sensor. So these take the form, as Saul has already said, of an industry standard iron core CT, the secondary of which is instrumented by our passive fiber optic sensing technology. And we call this device the photonic current transducer, or PCT. Now, this method allows the PCT to be monitored passively over very long distances from the interrogator location, and multiple CTs may be installed in this way per fiber at the transition platforms on the network. And that's how we were able to reach out and do this long distance multi-zone differential protection of those underground sections. So the next thing I want to do is just kind of zoom in on one of those transition points just to show kind of how we install at those locations and how we integrate into the existing fiber, and then how that data is kind of backhauled back to the interrogator. So the existing fiber bundle at the OPGW is routed down to a local splice box at the transition platform. This is the point at which the fiber from the OPGW is connected into the fiber from the cables to give you one continuous run of optical fiber. After that point where the splice is made in that splice box, that's where we put our passive optical sensors. So these are shown in split core format here for retrofit to an existing system. So we can just clamp these around each cable and then connect those into the fiber network using a simple loop out of the splice box. So it's important to note that there's no other supporting infrastructure required at that measurement location. It's only standard single mode fiber splicing to loop into that existing fiber network and mechanical mounting of those CTs at that location. As Saul said, there's no power supplies required, there's no active digital telecoms, there's no GPS access. So it's very simple and quick to install. Now, it's also worth noting, and I'll come to this a bit later on as well, that the sensor may be installed around the insulated cables on the lower side of the termination as shown here, which does not require a standoff insulator, or we can provide them with an appropriately rated insulator to install on the overhead side of the termination. And that's really a choice that's up to the operator depending on how far that protected section, that protected zone should extend. So as we've touched upon already, what Synaptec uses is a very familiar industry standard iron core CT for our sensors, not the optical type of CT that uses the Faraday effect. And our passive current sensing technology is simply connected to the secondary output of those CTs. So that provides a very low risk device that's familiar to any installer in the sector. So it's quick and easy to install. There's no sensitivity of the device to the way it is installed. And because we use industry standard CTs, we do not require to wrap fiber around the conductor or install additional equipment like multiplexers at that point. And as I've said, because each sensor is completely passive, we don't require significant civil works to install. There's no local power, there's no digital telecoms, GPS receivers. There's not even any copper wiring at that point. It's entirely just mechanical mounting and single mode fiber splicing. Now, another nice feature of our sensing technology is that as well as measuring the secondary current from each CT, every single sensor also produces a passive measurement of its own local temperature. And what this means is that we can actively compensate for changes to local temperature. We can monitor that in real time and then employ compensation on the measurement to correct for any temperature effects. And that gives us a very wide temperature range over which we maintain our accuracy. And finally, the optical side of our measurement is fundamentally based on a measurement of the wavelength of the light, as opposed to the polarization, which is what you get for the Faraday effect sensors. And that means that our method is very robust to fiber disturbances like twisting or looping, and it's immune to electromagnetic interference, which means that's really what allows us to reach out over these unprecedented distances from the interrogator to the end of the sensor array. And what that means really is that we can connect up to 30 passive sensor measurements per 60 kilometers of fiber, as Saul's mentioned already. And depending on how the fiber is routed, that essentially means that we can instrument multiple cable sections in series or in parallel. So it's a very flexible and very scalable system. We also offer sensors for various other parameters that Saul mentioned in the introduction, like voltage and temperature and vibration and strain and overhead line sag, any of which can be included in the same system as the rephase CFD solution, just to give a wider visibility at that point. So again, it's very scalable as a measurement scheme. So just to look at the PCT itself in a little more detail. So here there's a couple of different options shown on the screen. This is for the version for high voltage or medium voltage with a standoff insulator, if you're connecting around an air insulated conductor. And we also have the standard kind of low voltage version, which is appropriate for installing around insulated cables. The CT itself can be split core or solid core as required for retrofit or for new circuits. And we cover all standard transmission and distribution voltage and current levels. As I've mentioned, the temperature range for this device can be very large because we have that active compensation for any temperature effects. And we meet the standard metering and protection accuracy classes for this kind of protection purpose. Okay, so now I just want to kind of look at the full system. So that's a system that contains an interrogator and a series of current sensors deployed using the single mode fiber. So each system of multiple distributed current sensors and the interrogator allows us to deploy various different approaches to cable fault detection. The rephase interrogator itself can calculate both the kind of more simple ANSI 50G earth overcurrent algorithm or the full robust 87L differential current algorithm, depending on the operator's preference and their own best practice. And in some circumstances, we have been asked to do both on a single cable section, depending on the complexity of that circuit. And that can easily be accommodated as well, just due to the high number of sensors that can be deployed on a single interrogator. So we can really mix and match those two different approaches to give the best overall protection of that cable circuit. Now, because each rephase interrogator can monitor up to 30 individual photonic current measurements over a linear distance of up to 60 kilometers, this means we can provide full differential cable fault detection on up to five three-phase cables. So that would be 3 CTs at the start of that cable run and 3 CTs at the end, summing up to 30 in total on a single system. So this lends itself to various different interesting centralized cable fault detection schemes, which allows us to instrument multiple cable sections in series or in parallel from a central location, normally a substation. And I believe Saul touched upon this on the start as well, but if there are existing protection class CTs located at the substation end of any of these cable runs, we can of course deploy the passive secondary measurement technology to the secondary of those existing CTs. So that allows those to be digitized and then integrated into the same CFD scheme as our own primary connected devices further down the line. So I think this shows that this is a very flexible and scalable system for CFD and for adding on different functionalities on top of that. So I'll just pass back to you, Saul, now, just to sum up.
Okay, thank you, Neil. So what we wanted to demonstrate in this session was the concept that you can reach out far further than was ever achievable before with conventional or non-conventional instrument transformers. And as Neil was just showing, that it's quite simple to either retrofit or install new these sensors, which can be primary connected or secondary connected, leveraging infrastructure you've already invested in and installed, so that we can monitor multiple sections independently within a circuit. That could be several cable sections and dips running along the same line, which, if you don't think that sounds very likely, I can tell you we're actually working with a customer at the moment who's designing a circuit with 5 cable dips. So overhead, underground 5 times before it reaches the destination substation. And there literally isn't another technology in the world that could handle that across that range and that many locations. So it's about the scalability and the reach that we wanted to make sure people appreciate what this can do. Having said that, there is more information available here. Apologies, press one button too quickly here. So if you were to go onto our website, which is Synaptec, SYNAPT.EC, you will find a lot more information here. I did a quick screen grab for you covering the applications like cable fault detection and other uses of this technology. It also incorporates some product information and technical notes, and of course case studies and white papers that relate to usage by customers or thought pieces where we've published them in magazines like T&D World. We should also say that in addition to that, we've got a series of these webinars that are always recorded with notes, and we can always provide access to information about polling results and things like that. They're available on a private YouTube channel. So after this event is finished, we'll edit this session and publish it on the private YouTube channel and give you specific and indeed private and discrete access to that content for a while, so that you've got an exclusive use to review this. It's probably too much for everyone to take notes on in one big session, but the idea here is to say that I hope you appreciate that we've got a cable fault detection scheme here, which is very scalable and extensible and simply doesn't suffer from the challenges and deficiencies of other technologies because of our ability to scale up and go long distances. So with that in mind, I noticed that there were a couple more questions coming in here, and I saw one earlier on, which Neil has kindly already responded to, but I'm going to repeat back to everyone here because I think it's relevant and of use. And indeed, my apologies perhaps for not having kind of explained this. So we didn't really touch on the interrogator itself, and one of the questions was, well, what's your sampling or your publishing rate? Which was indeed an excellent question, which I should have covered. So the interrogator unit itself is a 3-unit high standard rack mountable 19-inch unit, which can take any standard industrial or common power input and simply needs access to the optical fiber, obviously to reach out and connect with all of the sensors in the array, but it also will have Ethernet ports so that we can publish and stream either IEC 61850.92 sampled values, or maybe we'll have sort of more traditional and conventional dry contact so that we can work directly with relays using analog connections. The sampling rate for protection purposes is by default 4 kilohertz, but in fact, we do have a higher publishing rate of 14.4 kilohertz, which is an option. That is specified within 61850 and 61869, so you can go either way with that. And of course, the higher the rate, the more information and detail is published. And typically 14 kilohertz systems would be taken by people who want additional information about things like electrical stress factors. So while there isn't a fault and we're monitoring a cable section, you might want to know about harmonics and power flow and power quality things, power factors, which might affect degradation or premature aging of the insulation or cause overheating effects. And that's part of the technology. It will also be able to identify these early warning signs of degradation and failure. And I should point out for everyone's information that the webinar that we're going to publish and invite people to next month actually goes into far more detail on that. So the next one in our series will be about how we use our systems to monitor cables and look for more failure modes far earlier than conventional technologies. But this hopefully will explain and answer the question that was asked previously, which is about the functionality and specification of the interrogator device. Fundamentally, it's 4 kilohertz or 14 kilohertz. Now, indeed, another question that has come up, which kind of joins up with this, so forgive me, I promise you I didn't plan this like this, it's just how people are asking questions. There was a question here about the differences between this and DTS. And if we go back to that slide where we try to show you conceptually, there's this unit here, which is effectively illuminating the fiber, and it's a single-ended system, and it will illuminate up to 30 different locations where we've got a spot measurement of something. Could be current, could be voltage, could be, in this case, temperature. And that might sound like DTS, but in a cable system, what we've discovered in our experience with offshore wind operations and subsea cables is that even if there's a DTS system installed, the DTS system is using the fiber kind of as a microphone to listen for things like hot spots and cold spots, like when a cable deburies and it's exposed to seawater, it might get colder, or if there's water ingress, it'll get colder, and a hot spot might occur if it's buried too deep and overheating itself, or there's a problem, like a fault brewing. Now, either way, distributed temperature sensing, therefore, is looking at, now this is my opinion and people have different opinions, but DTS is very useful because it will indicate if you've got a hot spot or a cold spot, and it's effectively looking for a failure in the insulation of that cable. And that can be incredibly useful, particularly for fault location. What we're doing is saying DTS is great to look at the consequences of failure and the signs of degradation from the outside, but our technology is looking at the electrical signal on the inside of the cable and trying to understand how that's interacting and causing those failures of the insulation. So where DTS is good for giving you a warning of a breakdown in the insulation layer, what we're doing is at an electrical level complementary to DTS, because we're looking for electrical faults and electrical sections. Now, in addition to that, there is a little bit of a crossover in those two fields. So firstly, it is possible, and it's an optional extra that can be configured into the interrogator that you see here, where we can activate OTDR. So this is optical time domain reflectometry, which simply means that we use the light source to illuminate those sensor arrays to notice if there's a break in the fiber, because we'll get a big reflection from an unexpected point. That has significant benefits because if you've already deployed 61850, instantaneously you'll get error messages saying that the signal from a certain number of sensors in the array is now no longer valid. And that's an immediate clue that comes straight through to the control and dispatch room to say, we now can't see some of the sensors in the array. And by interrogating that information, you'll be able to get a very accurate fault location if that fiber break is co-located with the phase conductors. Now, that is always true in subsea cables. It may not be, and in fact normally is not true, and they're not actually combined with the 3 phase conductors in the same package for underground cables. But there is an OTDR built-in fault location option in our systems. The other differentiator when it comes to monitoring temperature is, I think I mentioned this, but I'll stress it again, what we're offering is spot measurements. So very often at one of the weakest points on a cable system is likely to be the terminations. If they're imperfectly connected, or there are any pollutants breaking up the seal and causing air gaps and corrosion and therefore overheating, which can result in a failure, we're able to put our sensors directly onto those terminations and give a very precise measurement of the temperature just there. And again, because it's a digital system, that means we can immediately publish, for example, a 61850 goose alarm to warn of an overheating, because the operator will set a threshold for us, and then we'll set an alarm if the temperature exceeds that threshold, which is a simple thing to do. So it's, again, complementary to DTS, because that's giving you information all the way along a cable, but we're looking at the points of failure where often the DTS system isn't capable of instrumenting, and in fact often bypasses, which is classically the link box or a cable joint, for example, or a termination of a cable. So I hope that explains the distinction not only between NCITs and Faraday effect transformers, but also DTS. And we certainly don't pretend to substitute or replace DTS. We actually work with DTS providers because we think they're complementary technologies, and you should be doing both when you're instrumenting power cables.
Yeah. It's worth stressing as well, Saul, that DTS is a fundamentally different technology, because, as you say, it gives a continuous profile of the temperature down the fibre to a resolution of a few meters. And what we're doing is giving a very accurate spot measurement of temperature or current or voltage or strain. So they have very different applications, and they're both very good at different things. But you certainly couldn't use DTS, I don't think, for a terrestrial CFD solution, for instance. It wouldn't be fast enough and it wouldn't be accurate enough. So just to make that distinction.
Okay, thank you for that. And then another question that's come in here is about the accuracy range of this technology. So Neil, maybe you can go back on that and just readdress that point.
Yep, so it's quite a simple answer, really. So we offer all the standard protection class devices that you would normally expect for this sort of application. So the highest we offer at the moment is 5P30. Typically what we've seen is that's a bit higher accuracy than is required for CFD applications. It seems to be normally around about 5P20 or even 10P10 in some applications. But what we've done is we've qualified these current sensors for all standard transmission, all standard metering and protection voltage accuracy classes, I should say. So yeah, 5P30 is our maximum protection class accuracy, and 0.2 is our metering class accuracy.
That said, we should probably also add one caveat to that, which is that our preference as a supplier of this technology is to provide customers not only with this interrogator, but also the primary instrumentation devices, because that guarantees several things, not only quality and reliability with the installation of our sensors built into the primary transformer, it also means we've got proper control of things like saturation and dynamic range, which we think is very important, so we can guarantee that performance. That said, we have been asked, and we have indeed done this, where we've worked with existing CTs, for example, in a digital substation performing bus bar protection functions. And in that case, the existing CT is obviously providing that signal, and our sensor is connected to the secondary side of that CT, and therefore our performance and our accuracy is then governed by how good or bad that CT is that we're taking the reading from. So if we can secondary connect, but then of course some of the accuracy could be out of our hands depending on the primary instrumentation condition as we find it. That can be an issue, but it does have a lot of benefits to be able to leverage existing instrument transformers to get more information out from these locations. So I hope that addresses the questions of accuracy range. Now, there was another one here as we're talking to you, asking about the usage of this technology at levels of voltage beneath transmission, for example, 34 down to 15 kV. Now, the question that actually already kind of guessed what our answer was going to be. Typically, we find that fiber is not available below, say, 33 kV. Certainly true in the sort of secondary distribution systems. In the primary infrastructure of distribution, yes, there can be fiber, and certainly where there are towers as opposed to poles, we're expecting to find fiber availability typically around 95%. So it is true that this technology is not relevant and cannot help when you're in these medium to low voltage scenarios, because fiber simply isn't available. That said, the fiber does not need to be actually already available in the circuit. So if you're trying to reach out a small distance, or there is fiber nearby, because we have a budget of up to 60 kilometers of fiber per interrogator, we can use some of that budget to reach the location and reach back if it's useful. So sometimes the economics might not work out, and it doesn't make sense to run that fiber to those locations, but sometimes indeed we're doing a project right now where we do need to do that, and fiber is one location very close to the conductor, and we're just finding the optimum point to find the splice boxes, reach across like tens of meters, make a measurement and bring it back, because that's very convenient. It's just close enough to make good use of our technology. Otherwise, applications for voltage levels like typical of distribution, no, we have not done it. All our experience so far is in transmission, onshore, and then offshore, of course, that's 33 kV in array cables for offshore wind farms, or onshore wind farms indeed. That's typical. And we've also done some instrumentation, as I mentioned, in railways, which is 25 kV. But that's basically to take advantage of how a power system is divided up into relatively short electrical sections, and monitor those and the passage of trains through them, which can cause all kinds of faults and arcing problems and damage to the infrastructure as they pass. But typically it's relevant where the cost of the outage is very high, or the cost of manual intervention and in regular inspection is difficult, dangerous, or very high. And then the voltage level perhaps matters less. But yes, we are clearly constrained by availability of fiber in order to connect these sensors back to a central point. Okay, now I think right at this time we do not have any other questions queuing up that we haven't addressed. I hope I haven't missed anyone. I would apologize terribly if that I did. But I would like to say on behalf of everyone here and for everyone joining the call, that we were really grateful that so many of you took your time to go through this with us, and we hope that this explanation was of use. Please remember that this information is on the website. You can contact us and we can follow up with any more detailed questions afterwards. You can just use the email address of hello@Synaptec, or indeed info@Synaptec. Our website has a lot of this information up there. And as I say, after this session, we'll clean up this file, provide you with a copy of the recording on a private YouTube channel so you can review it at your leisure. And also you'll find, as I mentioned, the white paper that I was referring to on T&D World. And then when I think it's finished being published on there, we'll be able to ship that around to you, and you can simply ask for it on demand by emailing us. So we'd be very happy to talk to anyone of you who are interested in understanding how our cable fault detection systems could help you, and indeed save money by improving visibility and control for your business. Okay, so thanks again to Neil. Appreciate everyone joining us, and please keep an eye out for future correspondence where we'll be giving you the dates and timings of the next webinar session. In fact, I believe it's published now on our events page on our website. So the middle of next month, we'll be coming together again to talk about advanced techniques for ongoing cable monitoring for earlier warnings of future failures, which we think would be a very interesting application, and certainly already being used by one major transmission operator now to automate condition monitoring. So thank you, everyone, and looking forward to seeing you again soon. Appreciate your time, and please stay in touch if we can help you further. Bye now.
Thanks, everyone.